Hello everyone. So today, as per one of my viewers' request who commented in one of my previous video about bringing some rotational motion problems from Pathfinder, today I have brought you another problem. This is from Challenger Understanding, question number 3 from Pathfinder, and today we'll be discussing only one problem in this lecture. That is this one. So the question says you have a light rigid square plate of side length L which is suspended horizontally with the help of four identical vertical wires affixed at their lower ends on each of the corners of the plate. Okay. The upper ends of the wires are affixed to the horizontal ceiling and all the wires are elastic and have very high force constant. Find a region of the plate in which if you stick a load much greater than that of plate, every wire will remain taut. First of all, this line is very important. If you stick a load much greater than that of plate, we are basically said to neglect the mass of the plate. Neglect mass of plate. So this is the first thing you have to observe. The second thing is that it said that the wires are elastic. Wires are elastic and have very high force constant. This means that we can write tension as some kx, where x is the extension or the displacement of the lower end of the wire. Okay. So let's get started. We have done the required conclusions. First, we'll be drawing some xy axis, and suppose this is my square plate. Yeah, this one. Considering the diagonals as the xy axis. This end is L comma 0. Well, I'm considering L comma 0 as the diagonal. Well, it said that length is L. So I'm basically writing it as A comma 0. And A root 2 is equals to L. Okay. This is 0 comma A. This is 0 comma minus A comma 0. And this is the fourth point is 0 comma minus A. Right. Now I assume that this is the horizontal plane and downwards acceleration due to gravity is applied, and that downward symbol is given as this and the upward symbol is given by a dot. Downward is just the same way we represent magnetic field. We are representing gravitational field by a cross that says that it is inside the plane, and the dot represents outside the plane. So I am writing here the tensor as a dot, that will be T1, here it will be T2, here let it be T3, and here let it be T4. First equation will be about Newton's laws of motion, means that is F net is equals to 0. And well, we forgot to place the mass. Suppose the mass is here which applies a force in the downward direction and the weight equal to W. So weight is in newtons I am assuming, and the coordinates be x comma y. I can say T1 plus T2 plus T3 plus T4 is equals to W. This is equation 1. Now, writing the torque equation about the y-axis, I will get T2 T2 into A. So this force is this way, plus W into X is equals to T4 into A. T4 minus T2 is equals to Wx by A. This is equation 1. Similarly, T3, writing the torque equation along the x-axis. T3 into A is equals to W into Y plus T1 into A. Plus W into Y is equals to T1 into A. Similarly, T1 minus T3 will come out to be WY by A. This is equation 2. And this is equation 2 and this is equation 3. So we have four variables and three equations. We need another equation. You may ask me to find a torque about this axis. Well, the equation will get an equation, but this equation can be obtained by adding or subtracting 1, 2, 3 in some order or else. So it will basically be a waste of time. We need to think in some other way so that we can derive it. Now, if you look at the question once more, it is written that the region of the all the wires are elastic, which means that the rods will dip down by some height. Now assume this T1 dips down by x1, T2 by x2, T3 by x3, and T4 by x4. This diagonal is a line, so origin will dip by O dips by, where O represents the origin. Origin dips by, I can write that it will be the midpoint. Since it's the midpoint, so it will be x1 plus x3 by 2. It is equal to x1 plus x3 by 2. And similarly, this is horizontal x-axis diagonal. This will also dip down by, according to this, it will dip down by x2 plus x4 by 2, which can be written as x2 plus x4 by 2. Now, evaluating this equation, multiplying with k both sides where k is the force constant, I will get T1 plus T3 is equals to T2 plus T4. Well, this is a very powerful equation. This equation will help us to solve the whole problem. Initially, you may have seen an equation that is T1 plus T2 plus T3 plus T4 is equals to W. Now, just I am substituting T1 plus T3 is equals to T2 plus T4. I will get T1 plus T3 is equals to W by 2. T1 minus T3 is equals to W into Y by A. So if you write T1 is equals to W by 2 into 1 by 2 plus Y by A. This is equation 1. T3 is equals to W by 2 into 1 by 2 minus Y by A. This is equation 2. Similarly, other two equation we will yield you something like T4 is equals to W by 2 into 1 by 2 plus X by A, and T3 is equals to, sorry, T2 is equals to W by 2 into 1 by 2 minus X by A. Just check, there may be some problem in permutation. Well, maybe it will be T2 here instead of T4 and T4 here instead of T2. Doesn't matter because we need to make all of these terms as positive. Greater than 0, greater than 0, equal to 0, greater than equal to 0, and greater than equal to 0. So I will get the required regions as y greater than equals to minus a by 2, or y less than equal to a by 2, x greater than equal to minus a by 2, x less than equal to a by 2. Now this basically represents this region. Here let it be a square, and the shaded area I am marking it by green color. This shaded area is the required answer. You may be asked to find the area of the shaded region, so you may do it like this is a, this will be a by root 2, and this will be further a by 2, and this is a by 2, so this whole length will be a, and we already know a is equals to l by root 2, so it will be l square by 4. So hope you understand, or you can do something like this square. You just make the diagonals and use some similarity and all those to find the required result. So hope you enjoyed the problem. Thank you. Have a nice day.